still there. Let me change the slide. It doesn't even do that actually. All right, I'll just use the keys for now. Okay. Thanks very much, Hamza, for the introduction, and also to Raul, the co-organization of this workshop. So yes, this is a joint work with Ned and Hernando and Bauer, both at KAUST, and it's work on multi-level particle filters. I just wanted to present something that I've actually managed to do some research in the last 6 months, so I will present that. So it's a very simple talk, a very it's mathematical, not applied. So it's a very simple structure where I'll just talk about what I'm going to do, the modeling context, which is essentially the same one as Ibrahim's, and then essentially some methods for discretizing diffusion processes, followed by what is a multi-level particle filter, some approach and theoretical results. So this is essentially work for a particular class of state space models where the underlying process, the hidden Markov chain, is precisely a diffusion process in moderate to low dimensions, and we're not filtering anything above dimension 10. So this is really a small dimensional problem, and essentially we work under the constraint where the underlying diffusion process must be time discretized because, for example, you're unable to simulate it, you're unable to evaluate the exact transition dynamics of the process, and so we resort to stochastic discretization methods of this underlying diffusion, and this is a new kind of multi-level particle filter that basically is reducing cost to achieve a given mean square error, MSE mean square error. Okay. So the context where it's really useful, what's the point of this work? Well, it's useful in this particular context where the underlying stochastic differential equation, the SDE, is in dimension at least 2, so that's good. So you have that, and the diffusion coefficient is non-constant. So otherwise, we're not doing anything better than what was in the literature already. Okay, and so of course this is not going to apply universally to every diffusion problem. That you have has to be sufficiently well behaved. In particular, you have growth and Lipschitz conditions on the drift and diffusion coefficients. I put bounded coefficients, but that's really for the mathematics, which I'll say a little bit about. And essentially, the idea is very simple. For those of you who work in the field, you will see the idea already from this slide, but if you don't, then it doesn't matter too much. The idea is essentially to embed the notion of the Milstein. So you want to use a Milstein scheme, and those of you who've used the Milstein scheme know that in dimension 2, 3, 4, 5, and so on, that you really can't apply it because of the fact that you have to evaluate this Levy type integral, Levy area, sorry. And so there is a method which says, okay, I don't know how to do that, so I truncate the Milstein scheme, I remove this Levy area, and you go back essentially to discretization methods which are of order 1, like the Euler Mariana method. But essentially the point here is that then you can get rid of it. You can go back to Milstein by using the multi-level Monte Carlo method. Okay, so that's this nice work by Giles and Spruce back in 2014. Okay, but in order to embed that in a particle filter, so this just essentially comes from a referee report that we got one of our articles saying, why don't you embed this scheme into your multi-level particle filter? And the answer is it's not very easy to do. So it takes a lot of work, not only to actually algorithmically apply this technique to essentially realize the gain of this Milstein scheme, but not only that, but then to show it actually does something sensible. And so essentially that's what this presentation is all about. So the model is very simple. You have two aspects. The equation 1 represents the data yt, which is associated to an unknown hidden stochastic process xt. Okay, so YT are taken to be observed discretely in time. We'll put unit times. It doesn't have to be unit times. It doesn't have to be regular, but I like it for presentation purposes. So that's the equation 1. So epsilon t is a sequence of IID, zero mean process of a Gaussian, for example. And the underlying hidden process is a diffusion continuous time process. That's equation 2. And so when I was talking about coefficients before, I was talking about this, which I suppose will be alpha at some point, and beta, which are the drift and diffusion coefficients, respectively. And so just as in the previous talk, what we're trying to do is we're trying to estimate xt or functionals thereof conditional on the observations y1 to yt, y1 to t, where the observations are observed regularly in time. Okay, so that's the filter. Okay, so I'm going to see the y's and I want to work out what x is sequentially and recursively in time. It's no different to what we were doing in the previous talk. Okay, so the filtering problem can be defined through this joint distribution on the hidden states in discrete time. So you have the discrete skeleton of the x's. So this is the process, this is the transition dynamics of the diffusion process. And then you have some observations, G, represented by the likelihood, which is assumed to be available up to some constant independent of x. Okay, and so this defines a joint distribution on the x's and the y's. And so if I integrate all the x's from time 1 to time n minus 1 and normalize, I'll get what is known as the filtering distribution. Okay, so that's the next slide here. So this is the filtering distribution. So I just integrate out the first k minus 1 coordinates and divide by the integral over the whole k. And so this is a dimension, giving you the filtering distribution, filtering density is exactly what you saw in the previous talk. And the normalization constant is also called the marginal likelihood in statistics. Okay, and so all I want to do again is to compute or be able to approximate this distribution recursively in time k, where k is a discrete index, and or compute expectations with respect to such a distribution. Okay, and so the key point, as I mentioned at the beginning of the talk, is I'm assuming that P is not available analytically. So I can't get it. If there's a density, I can't get at the density. I can't simulate it exactly, even if there is a by now a whole battery of exact simulation methods for diffusion processes. And so what I'm going to do, as we frequently do, at least in my work, is to work with a time discretization, which means in between each observation time, 1, 2, 3, 4, there's basically a grid of the diffusion process, equally spaced at times 2 to the minus L. So first of all, I'm going to have, so x0 is known, then I get 2 to the minus L, 2 to the minus L times 2 to the minus L plus another 2 to the minus L, plus another 2 to the minus all the way, and I get to 1. And then basically that's my discretization, which is responsible for the approximation of the process, which is described by P. So I'm essentially approximating P with a discrete time process and then integrating out those unknown points. Okay, and so what we're going to do is we're going to approximate P with PL, say, where L is a discrete parameter, and that PL, approximating P, is going to be this truncated Milstein scheme. And to say, so for those, again, there's a lot of you in this room know exactly what these methods are. The truncated Milstein scheme is exactly as good as Euler-Maruyama. It's no better in terms of strong error. Okay, so there's some notations here. It's actually not that important. It's really just to show you that there is a scheme there. So there's a vector H. You can see this definition here. It's not important what it is. The key point is that basically, in order to use the methodology to be described, I need to be able to compute some derivatives of the diffusion coefficient. Okay, so this is explicitly assumed. If I can't get at these derivatives, you can forget about the rest of this talk. This is assumed. If I can get at these derivatives, I can get hold of this function hi, small hij(k), and I can substitute in here. And it's not important what exactly is this expression. It's just to tell you that I need to be able to get a hold of the derivatives of my diffusion coefficient. Okay, and then some notation, which is a standard for me by now, is I'm using this to represent a d-dimensional Gaussian with mean vector mu and covariance matrix sigma. Okay, and then if you want to put the identity matrix in, you put ID. Okay, it's just a notation, just to tell you. So what am I going to do here? I'm going to describe what is this truncated Milstein scheme. So it just tells you, okay, I want to approximate the solution of the diffusion at time 1. I can't simulate from time 0 to time 1. So I'm going to generate a grid of points at time 2 to the minus L, 2 to the minus L, plus 2 to the minus L, and so on and so forth. And at the end, I have a point x1 on the which has been simulated from the grid. And that point x1 is not exactly from the diffusion, but it'll be close. And it will get closer and closer as I make my grid finer and finer. Okay, and so the simulation is just like this. So I have the amount, how much simulation I want to produce, okay, which is L. So as L grows, that's going to cost me more because my grid is getting finer and finer. Some initial point, which in my model is assumed to be known, but subsequently we will need to be able to do it with a given initial. With a different starting point, and the way it works is very simple. So you just generate a collection of Gaussians, d-dimensional Gaussians, okay, where basically the cost of that simulation is of order the number of grid points. Okay, so that's the thing here. So that's where the cost of it is coming from. Okay, and then to just basically generate the process. Well, for those of you who are specialists in the field, this first part here, that's just the Euler-Maruyama discretization. And this extra bit here, this vector H, is the definition on the previous scheme. And basically, it's like the Milstein scheme without the Levy area. Okay? Okay, and it's a very simple, so this is a very simple scheme. If I can evaluate, so here alpha is A. I think I made a mistake with my notation, but alpha is this is the diffusion drift, this is the diffusion. So I need to be able to evaluate the drift of diffusion, some derivatives of the diffusion coefficient. Okay, and it's a simple recursion. I can run this for the order of the number of grid points, and I output this point here. And if L grows, as L goes to infinity, x1 will be exactly a sample from the diffusion. Okay, so it cannot be exact. It's never going to be exact because I can't run an infinitely many number of grid points on my computer. Okay, so this is the truncated Milstein scheme. And again, as I say, this has been around for a while. It wasn't Giles and Spruce that came up with it, but it was them that managed to realize that you could still recover what was good about Milstein from this scheme. Okay. So this is just approximating the unknown process. Okay, and so what we're going to do in our modeling framework is we're not going to work with the original dynamics of the diffusion process. I'm going to work with an approximation thereof, which is this thing here. So this is basically this piece superscript L. What it is just a simulation. That's just a realization of the previous algorithm, the algorithm on the previous slide, where I input x as my initial point, and I run over my delta L to the power -1 grid points, and I produce my point x1 L. Okay, and so what I'm going to do is, instead of working with the thing that I had at the beginning, that's the original model here, if you like. This is the original model here, which is essentially a simple hidden Markov model. I'm not going to work with this. I'm going to work with this one here, where basically the only change is I'm using this truncated Milstein scheme to define this transition kernel. Okay, and so now what I have is when I try to do filtering, which is hopefully what I have on the next slide, when I'm trying to do filtering, I'm doing exactly the same thing. So I still have a state space model. I just have a time discretization of it. Okay, but I've got the wrong state space model. Okay, so this filter here has a level of approximation. So K is the time, that's the data index. So time 1, 2, 3, that's data time. But L is now the level of discretization of my hidden process, of my truncated Milstein scheme. And this is the normalizing constant, which I'll keep on telling you about. And I can approximate, but I never tell you in this talk how to do it. Okay, and so what's new here? There's nothing particularly new here, right? If I try and do the particle filter or the multi-level particle filter as it was in some of the existing literature, I'm going to do exactly as well as if I used Euler-Maruyama. That is to say, if I just ran this part, these first 3 terms here, and I forget about this one, it's essentially the same thing. I don't do any better, right? So when I say I don't do any better, what I mean is I don't do better in terms of reducing the costs. But what we're going to show is that how can we leverage upon that nice work of Giles and Spruce to really reduce the costs. So that's really the idea here. So the motivation for this scheme is, as some of you know very well, is the well-known Milstein method, which for stochastic methods of discretization is the best and is indeed optimal in a Monte Carlo sense. We know, however, that basically, and of course, we're assuming here that what we're trying to do is we're trying to approximate the Milstein method. And as I said a couple of times already, I'm assuming that I can compute those derivatives of beta. But the key point is, as I said, and this is the idea, this is where it comes from, is in many cases the exact Milstein method is not available when the dimension is 2 or 3. I think it's 3 is definitely not true because of these Levy areas, Levy volumes. Okay, so what we're trying to do now is we're trying to get over this hump of basically trying to get Milstein without doing exact Milstein. That's the idea, if it helps you. And so, if you, as I said, if you do truncated Milstein, and it's been studied in the literature well before I ever looked at it, it's just, as I said, the same as doing Euler-Maruyama. Now, Euler-Maruyama is slightly cheaper and easier and more applicable because I don't need any derivatives. So the question is now, why do we consider truncated Milstein if it's no better than doing Euler? And so, as I said, so this is the conclusion. Is, you know, I've been saying it the whole talk, but essentially, if you use, or you can use a multi-level Monte Carlo method, which basically says, even though I don't calculate this Levy area or this Levy volume, I can still get rid, or I can get back to the strong error rate, which is what I'll talk about in a moment, of the original Milstein scheme, which would be optimal. Okay, and that's what we're trying to do. We're trying to recover as best as possible. We still won't be able to do it, but we'll get close. So now what I'm going to do is I'm going to tell you a little bit about this method of Giles and Spruce. It's quite old, actually, but well, relatively old, but it's still quite interesting that it works so well. And so essentially it's based upon what are called antithetic variates. And for those of you who are statisticians, you know that very well. And if you're not, it doesn't matter too much. It's just a little bit of a reflection type of approach. And so in order to describe this method, what I'm going to do is I'm going to talk about trying to compute differences of expectation. So in this slide here, this represents the solution of the truncated Euler-Milstein scheme at time 1 with delta L to the power -1 points. And this is the expectation of the solution of x1 under the discretization with delta sub L -1 to the power -1 points. Okay, so if you prefer, this one has twice as many discretization points as this one. Okay, but the thing that they're approximating, of course, is a d-dimensional quantity. Okay, and that's what it says here. Okay, and so what we're going to do is we're going to show you how this thing can be approximated using this truncated Milstein scheme, antithetic truncated Milstein scheme, and then you can recover back Milstein. That's the idea eventually. So the idea here is always in this type of multi-level Monte Carlo scheme. If I can sample a good coupling, what I mean a good coupling is some joint distribution on these pair of random variables, such that the marginal in one of them is this one, and the marginal in the other variable is this one, but there's some joint dependent structure. So that's what I mean by coupling, and it's good in some sense, because what I want to be able to do is I want to obtain a sampling of that joint coupling so that I can reduce the cost to compute to obtain a certain given mean square error versus using ordinary Monte Carlo methods, where I simulate the two pairs of random variables independently. Okay, so if it's unclear to you what I mean by this is I sample a pair. There's a missing one here and a missing one here, but I sample a collection of n samples. This is a d-dimensional random variable. This is a d-dimensional random variable. This is representing the solution at level L, and this is representing the solution at level L -1, both at time 1, and there are n of these samples, okay? And so I want to be able to do that in such a way, such that if I look at the expectation of difference of the square, okay, so of course this is an appropriate metric here, L2, okay, that this thing is suitably small. So this, what it tells you is I send L to infinity, i.e. the number of grid points get larger and larger, this thing goes to 0 suitably quickly, okay? And so at the if you just do standard coupling of the truncated Milstein scheme or the Euler-Maruyama, and that's basically based upon the synchronous one, i.e. sampling those Gaussians are suitably correlated or suitably replicated, then beta is equal to 1. Okay, and that's what you get from Euler-Maruyama. Okay, you get that from the convergence of the diffusion process, in fact. Okay, so then what's the point here? So what's the point is what we're going to do is we ultimately want to approximate the expectation of the law of the diffusion process at time 1 at some suitably fine discretization capital level capital L. Okay, so that's what I want to do. And so I can rewrite this as a simple collapsing sum representation. Okay, and so what I'm going to do is I'm going to show you how you can approximate that. First of all, the level 0 is simple, but the other ones using this antithetic truncated Milstein scheme. Okay, so at level 0 is very simple because there's nothing to do. There's no coupling, there's no differences. I just simulate N0 samples IID from the truncated Milstein scheme. So it doesn't have to be 0. You can start something a little bit later because in fact there's only one point to simulate at level 0. And then at subsequent time points, subsequent discretization points, so now there's a difference in here. And so what we're going to do is independently from L, for each L sample, N IID samples from this coupled truncated Milstein scheme, which I'm yet to tell you what it is. And so that's what I'm saying here is that the coupling can be constructed and is given later. Okay, so that is, so here I'm saying that the strong error rate beta is 1 for the standard truncated error, truncated Milstein scheme, which has been coupled, and the coupling is to be described later. And so if I choose the number of samples at each of these levels, L and L, suitably like this, and I choose the final level suitably like this, then in order to obtain a mean square error, so the error of an estimate, so what I'm saying here is that there's a way to construct a Monte Carlo estimator using this scheme of basically this identity and ultimately of this, okay, in such a way that the cost to obtain the mean square error of this thing as order epsilon square for epsilon greater 0 and arbitrary, and it's going to cost you this because basically you have a strong error of 1. Okay, and if you're not familiar with this, all I'm saying is essentially you have a method to approximate this using capital N0 samples. Now you have a method to approximate this using a capital NL samples, and if you choose capital L and a number of samples NL appropriately, you can do better than the ordinary Monte Carlo method, which would cost you order epsilon to the -3. Okay, this is well known, I know, for at least half of this audience, and if you don't know it, I'm explaining it well enough. Okay, and so that's using the coupled truncated Milstein scheme, which I haven't told you about, but I mean, for those of you who, again, are specialists in this field, you know exactly how it's been simulated, and if you don't, we're going to talk about that later. And the reason it's not optimal, the optimal thing would be that if you got a cost of epsilon -2, well, that's the best you can ever do with Monte Carlo methods because of the way it's set up and the asymptotics and mean square errors. And so what I'm going to tell you now is how you can actually get that from beta is equal to 1 to beta equal to 2 using this method. Oh, sorry, they've gone to the wrong slide, and I'm going to pay having gone all the way back to the start. Yeah, sorry about that. So the idea is that this Giles and Spruce paper said, well, instead of having beta equal 1, you can get beta equals 2, and you still don't have to compute those Levy areas. I mean, that's the thing idea. And so they combine Milstein and multi-level Monte Carlo and antithetic variance. So here is the algorithm. It looks like it's horrible, but it's very simple to simulate. Right? This is why I'm just describing the simulation and not the transition kernel, because I could write that for you and our brains could explode and there would be no point in talking about it. So what you need here, so in order to approximate the differences, I need three things. I need something at level L. That's going to be my initial point at level L. I need something at level L -1, and I need something at level L with the superscript A, and that A is representing what's called an antithetic variance. Okay, and so I'm going to simulate 3 paths: one at level L, one at level L -1, and one at level L again. But the one at level L is this antithetic path. Okay, so the way it works, so at level L, let's highlight this better. At level L, I generate 2 to the power L Gaussians. Okay, that's what you can see in that thing. And you just run the recursion. This is just this recursion. This is the truncated Milstein scheme. Okay, that's just that recursion I talked about earlier. So you just run this scheme. It can be done very fast in a computer, nothing difficult here. Okay, then at level L minus 1, I'm going to use the same Gaussians. Okay, so this is basically, this is the discretization at level L minus 1. Looks horrible, but basically this sum here is essentially using these Gaussians as before. Okay, and they have to come into H as well. Okay, so this is, for those of you familiar with the synchronous coupling of Euler-Maruyama, you need to sum the Gaussians to get the discretization at level L minus 1. So here, this is basically what you would do if you wanted to couple truncated Milstein, of which there is no point because you could just do more Euler-Maruyama. It's the same thing. The key observation of this Giles and Spruce algorithm is you need another one of these L's. This is called the antithetic variance. And so this is essentially the same idea. You run the same, you've only got one sequence of Gaussians, which of 2 to the L Gaussians, right? And I've used those 2 to the L Gaussians at level L. I've used the same 2 to the L Gaussians, except appropriately summed at level L minus 1. And then basically you use them again, but you use them in here. And these are basically a kind of, it's hard to describe it without actually showing you how to do it. Basically, you're flipping the order of these Gaussians around. It's the same sequence, just reordered of Gaussians, if that helps. This is the mathematical description, which I do not expect you to follow at this time point. But basically, it's just still those 2 to the L Gaussians flipped around. Okay, and it's very simple to simulate. You don't have got to do anything very complicated there. Okay, and at the end of this scheme, you get 3 d-dimensional vectors, one at level L, which represents the solution of the diffusion at level L, the solution at level L minus 1, and then this antithetic one, which is basically the discretization at level L, except with the so-called antithetic scheme.
What's the idea behind flipping this stuff?
It's an antithetic, it's antithetic variance. Well, that's what you do in antithetic variance. You reflect the things around. That's
just like you start with the last Gaussian and then the one.
Yeah, it's if you think about the grid, you're flipping them around instead. So if you had like a delta L and 2 delta L, then you use the 2 Gaussians, but you use those ones flipped around, and then you do it again, and then you do it again, and then you do it again, and that's what antithetic variance is.
I think that's some condition.
I don't think so. They only need drifts, and I don't believe so. I have to check the paper, but I don't think that they needs it. You might be right, but the last time I checked the paper, I don't recall. I read the paper quite a lot, so I don't believe so, but maybe you're right. So then what's the point of this? Well, they say, okay, now if I want to recover the strong error rate of Milstein, what I do is I take this one plus this one divided by 2, and they approximate the same thing. This approximates the solution of the diffusion at level L. This is an approximation of the solution at level L. So if I add them together and divide by 2, this approximates the solution at level L. I take off the solution at level L minus 1, I square it in the correct norm sense, and I take the expectation over with respect to the distribution of the randomness that I just talked about in the previous slide. Okay, and I get again another delta L to the beta, but the key point here is beta is equal to 2, not 1. And that's critical, because the reason it's critical is because basically once you have beta equal to 2, you can take a different ordering of the samples, and what you'll do is in your multi-level Monte Carlo, instead of having order epsilon minus 2 log epsilon square, you get order epsilon minus 2 as the cost to obtain this mean square error. Okay. And that's the idea. So essentially what we want to do now is I want to use this scheme. So there was no data, there's no filtering in this, and I want to use this now in terms of filtering. And like I said, this was one day referee put in this here, why don't you use this method? This is why you don't use this method necessarily, because it's not very easy to do. Okay, so now what I'm going to do is I'm going to describe the multi-level particle filter, and then how you use this scheme within the multi-level particle filter, and you try to recover basically what Giles and Spruce did. Okay. Just some notation to begin with. That's not important, but this is basically, they're going to be a collection of functions where I want to basically compute statistics of those functions in my filtering. So I'm going to just constrain myself to a collection of bounded and measurable functions. They don't have to be. And then my notation is that if I can want to compute the expectation with respect to my approximate filter, and approximate because of the time discretization, I just write this, I just use this notation, which is pretty standard in the probability. Okay, and then I'm going to have some upper and lower levels. This is like, so here I was using level L under bar was 0, and I was using L for L over bar, and it doesn't have to be like that. It's just basically going to be given. And what I want to do is I want to sequentially approximate the filter at level L bar. Okay, and this is just some notation, but it's not important, but that's what I want to do. Okay, and you knew that. Hopefully you knew that. If I was saying anything that made sense, that was what was hopefully the thing that did. Okay, and we're going to, again, we want to leverage the multi-level Monte Carlo identity. Where this is now the only difference between this one and the one you saw before, excuse me, is the fact that here I'm going to have some data, but before I didn't have any data. Okay, and now what I want to do is I need to be able to approximate each term in the sum and sequentially in time. So this one will be easy in some sense, and the other, these ones will be more difficult. Okay, so we begin first with approximating the expectation at the lowest level. Okay, and this is going to use a standard particle filter. And again, as discussed in the previous two talks, this is really a low dimensional scheme. So it works very simply. So I have n sub underbar L samples. And what I do is I generate the first one, or all of them, if you like, independently using the truncated Milstein method, okay, which is just basically simulating Gaussians. So if I have a grid of size 2 to the L under bar, and I just simulate 2 to the L under bar Gaussians, and I put them through a recursion, which I assume I can evaluate. Okay, there's nothing difficult about that. I do that independently, so I is the index of the sample or particle, if you like. Okay, and so I've setting k equal 1 was my iterative sample. Then what I do here is something called resampling. So I compute these n weights, capital N weights. This is a probability distribution on those n samples, and they basically, if I have this representation, these samples, I can compute approximations of the filter at time k here, k equal 1. Okay, I can tell you how to do that, but I don't think that's too important to you. And so in this step, once you compute this, what I do is something called resampling, which is I generate an index ak sub I using the probability mass function here. So this is a probability mass function. So I say I pick this first sample with this probability. I pick the nth underbar sample with this probability. So this thing is one of these values 1 to nl bar, and then I do that independently for each of them, and I have then a collection of samples where I've replaced basically now my new samples are the old ones, and so the number of indices that are sampled is a random variable, so I could have 5 of the first particle, 1 of the second particle, none of the third particle, and so on and so forth. The total number of samples is fixed. Okay, so I'm just doing that. Okay, and there are, for those of you specialists in particle filters, there's reason for doing that. If you don't understand it, it's not important. It's just it's a method. It's a step of the algorithm which is a necessity. Otherwise, you cannot do anything simple with it. And then what you do is, at subsequent time points, you're going to move the dynamics. So here I have my samples. I got them from my resampling step, and I generate all the new ones using the truncated Milstein scheme conditionally independently. Okay. So that's what they call the forecast step in data assimilation, and the update step is this. This is the update step, or the assimilation step in particle filtering. Okay, and so now, if at any time step, and I keep on going for as long as I like to do it, okay, I can do that, and as long as the dynamics are suitably well behaved, this is a time uniform approximation of the filter, and the time uniform approximation is this one. So this is my weights. This is my functional. I just have to be able to evaluate point-wise the likelihood function of my observations given the current state. And it's fairly standard in the literature, so it's going to converge no matter what happens to the model. If I send NL to infinity, NL bar to infinity, and it will be time uniform if the diffusion is suitably stable with respect to, or the discretization is suitably stable with respect to time. Okay, and so again, in order to do that's all I've done here is I've shown you, if you didn't know already, how you could approximate this first term in the in this multi-level Monte Carlo identity. We've been well known for at least 15 years by now, probably about longer. Now what I want to do is I want to discuss how can I approximate these differences. Okay. So the multi-level particle filter MLPF method of 3, which was work that we did a long time ago, it's published in 2017, samples basically couples of Euler discretization and the maximum coupling of the resampling indices. Okay, so what does that mean? What it means is that what you're doing here is you're working with pairs of discretizations, one at level L, one at level L minus 1. So what that means is that in order to simulate this thing and trying to recover some of the strong error properties of my discretizations of my processes, is I need to be able to run this forecast step, if you like, which is coupled. Okay, but I know how to do that for truncated Milstein. I know how to do that for Euler, and I also know how to do that a little bit with the antithetic method. And I also have to have pairs of so here I'm resampling one index, right? But I have two pairs of particle systems, so I need to be able to couple the sampling of the indices, and you can do that with what's called the maximal coupling. Okay, I'm not telling you the details, but that's what we did back then. Okay, and it works quite okay. The problem with it was that method of resampling loses half the strong error rate because it's not an optimal resampling method in any sense, as I showed in some previous work. So what we're going to do now is how we can extend that method so that I can now use that antithetic truncated Milstein scheme, but I'm still going to lose this thing. And essentially, with the method that I'm using for resampling, I'm always going to lose half the strong error of the diffusion. I'm always going to do that. And in some joint work with Raoul and Eric who are in the audience, we managed to get rid of that problem, but only in one dimension. And this method is only useful in dimension 2, 3, 4, or so on. So we still are stuck with that same problem. Okay, so what I'm going to do now is I'm going to show you how you can do the resampling of 3 indices. Okay, it's not very difficult or very well. It's not easy to think of it actually, but it took some time. But basically what you need is a mechanism to resample those 3 indices so that there is some correlation between those resampling indices. So what I'm doing is the problem here is very simple, right? So I don't put the problem in full generality. What I have is a collection of 3 vectors and n things. Okay, so I have, let's say u1, u2, u3 are in dimension 1, and I have n of them. Okay. And I have a collection of probabilities associated to them. Okay, and what I want to do is I want to resample the U1, U2, U3 in such a way that marginally the probability that I pick U1I is W1I, the probability I pick U2I is W2I, the probability I pick U3I is W3I. But the simulation of those indices is sufficiently correlated. Okay, that's the problem that you have to deal with if you want to use this antithetic truncated Milstein scheme. Okay, and this is how you do it. And again, it looks very, very difficult, but it's not that difficult because you only have to simulate uniform random variables. So what you do every time, so this is how you simulate one index, well, a collection of 3 indices in one go. So I sample, so this is I, so I generate one uniform on 0, 1. Okay. Now, what I do is I compute the sum I is 1 to capital N, or the minimum of these probabilities. And if U is less than all of these, then what I'm going to do is I'm going to say all these 3 indices are equal. And the index that they take is generated according to this probability mass function. This is order n calculation. Well, it's order 1. Actually, it's order 1. Yeah, it's order n because you have to compute that. Okay. And so that gives me my index for my first index. Let's say I is equal to 1. I've got my first index for all the 3 samples. But if this didn't happen, I need to go and do something else. And that other thing is I'm going to have to sample these 3 indices using any coupling of this probability mass function. Is typically independent coupling, right? It doesn't have to be, but it can be independent coupling. Okay, and that's going to be 3 numbers in the set 1 to n, and they could be equal, they could be different, but they have to have this probability mass function. Okay. And so if you do that, and then you output all of your samples. Okay, so you basically you started with U1 1 to n, U2 1 to n, U3 1 to n. I run that, I resample my 3 indices n times, and I have a new collection of samples. And those collection of samples are such that the ones I've resampled for this subscript have this probability mass function. The ones I've resampled from this index have this probability mass function, and so on and so forth. And that's essentially what you need to do in resampling, or the resampling operation of the particle filter. Okay. And what I'm doing here is I'm trying to replicate, for those of you who are specialists in probabilities, is to replicate the maximal coupling. Well, this is not a maximal coupling here in any sense. Okay. But given this method, I can now essentially implement or incorporate the method of antithetic truncated Milstein into the multi-level particle filter. So how does it work? So what I do at the beginning is essentially run that antithetic truncated Milstein scheme, okay, which consists only of simulating 2 to the power L Gaussians and computing some derivatives. So I just run that through my, just run those and I do that n sub L times. Okay, so the level here is, well, here it's supposed to be L, I think, not n sub L, but anyway. Okay, then what I do is I need to compute my 3 collection of weights. Okay, so these are the correct weights. If you want to know why, we can talk about afterwards, but these are my 3 probability distributions. And then what I do is I'm going to simulate my collection of samples, these collection of samples from these collection of weights using the scheme that I discussed in the previous slide, previous 2 slides ago. That's what I call the 3-way resampling scheme. Okay, and so then that gives me basically my n samples where I have the collection of 3 things, and now I need to go and do the forecast step, and the forecast step is run using antithetic Milstein with level L. So that's what you do here. Then you increment the time step, and you go back, and you keep on going for as long as you like. Okay. So to conclude, what is the method? I know there's a lot of indices and ideas here, and I tried to make it as painless as possible, but I find it's always very painful. The idea is the following. So at level L under bar, that's my lowest level, I run my particle filter. Okay, and at any of the other subsequent time points, I run this, what I call the coupled particle filter. Okay, which is the scheme that I just described to you in the last couple of slides. Okay, and now I can approximate my multi-level identity by basically using these weighted averages. This is a weighted average. These ones are the weighted averages which have been computed. I don't know if I wrote the expression. I didn't write the expression. I didn't write the expression. But anyway, these have been computed using my coupled particle filter at level L. Okay. Right. So that's how you. So you can see. So there you see. So there was 1 referee comment, and there was 8 months of work. So that's what tells you never listen to referees. Don't listen to all referees, yes. Okay, so then there's a result. Doesn't matter basically too much what this thing looks like, but what it tells you is you have the filter. I want to approximate the filter. I have my approximation I discussed on the previous slide. These are one-dimensional things. I square them, and I take the expectation with respect to the uncertainty in the system, and I get an upper bound. Okay, and it doesn't matter what this upper bound looked like. It's a monster, and it's a monster for a reason, because it's very difficult to prove this upper bound. I know because I proved it. Okay, so there's an upper bound. But what does it mean? Well, what it means is the following. You have your epsilon. You want to achieve an error of order epsilon squared. Your epsilon, whatever you like. Let's go epsilon squared. Now, what I'm going to do is I'm going to choose my highest level so that my weak error, and that's my bias, is of order epsilon. So that's the same as you did right at the beginning. There's no difference there. And now what I need to be able to choose my intermediate samples. So I need the first one's going to be order epsilon -2 because I can't do anything with that. And these are my other samples here. And this thing here is basically what you have for the very original first thing with truncated Milstein. So if you do that, you get if you plug these parameters into the bound that I showed you on the previous slide, you get a mean square of order epsilon square. And it turns out the cost to achieve this is order epsilon -2 log epsilon squared. Okay. You're going to say, so what? Well, Why is it interesting? Well, it's interesting because if beta, the diffusion coefficient is non-constant and the dimension is 2, I think it has to be 2 or more, or 3 or 2, bigger than 2, or at least two or more. If you go back to the scheme that we introduced a while back on multi-level particle filters with Euler-Maruyama, you would get a cost of epsilon to the minus 2.5. So it really does improve upon what we had before by quite a bit. Okay. And if you want, I could show you the plots which confirm exactly this finding, but it's not going to be any different from that you see in front of you. So that was, I mean, that was it. I mean, that was all I wanted to say about that. So essentially what we did is we presented new multi-level particle filtering for filtering diffusions. The only thing that we do is, the only thing we managed to do with all of this work is that if you are in dimension 2, 3, 4, or you really only go to dimension 10 with particle filter anyway, that you reduce the cost from epsilon minus 2.5 to epsilon minus 2 log epsilon squared. And it's not the Milstein rate because the resampling scheme that we use is not optimal in any sense. We don't know how to do better than that, except in this work that we did with Eric and Raoul when you're dimension 1. And so that's kind of, there's no point in using it here. And if you're interested, actually read the details, because there are a lot of details and you didn't tell you about, because essentially, you want to stay awake for some time. You can go to the archive paper, which we put in January. Thank you very much for your attention.
Thank you, Ajay. Questions? Yes, please.
Next time you have this one.
Yes, thank you very much. Just a small technical question. How you choose epsilon square for MSE? I think it's based on.
So you just chose, that's the amount of error you want to achieve. So if you want the error to be 0.001, then that's how you choose epsilon. I mean, it's within constraints, of course, because you may not be able to achieve it. But
I was thinking if I have different quantities of interest, and this epsilon square depends on quantity of interest. Yes, it could be 100 or maybe 0.1 and so on.
The bound will depend on the quantity of interest, yes. Since I'm using subnorm, it's going to depend on the subnorm. So that will tell you the order. Yes, it's an order result. It's not an exact result. So the order of the result of the error will be epsilon squared. So for some test functions, it might be 100 times epsilon. Some test functions might be 0.1 times epsilon squared. So if you want to do that, you need to know a lot about the function, which generally in filtering you don't. But I see what you mean. Yeah, but it's an order result. That's all you know. I see what you mean. But that's the best you can do with this kind of methodology.
Thank you.
Any other questions? Yeah, can you throw it?
Miss.
So what is it exactly?
Little g
So that's the so if I go back to the original model,
from the data.
There you are. So this thing, little g, is defined through. You have to assume that you can get it from here. So epsilon t is an IID sequence. So if you give me x, I should be able to find the density of y given x. So for example, if y was x plus epsilon, then you could get an epsilon was Gaussian, you get a Gaussian density. So it's a modeling assumption.
It's the likelihood of the data.
Pi. This is pi. So pi is the filter. So pi is, so in order to get the filter, you need both the likelihood function and the dynamics. And you put the dynamics together and with the thing, and you get this. You put the dynamics together in a nonlinear fashion, and this is the filter that you get as a result of it. And this is the thing you want to approximate because it represents the conditional density function of the hidden signal at time k, given the observations from time 1 up to time k. And so, as I said, the G is a modeling. You have some real data. You decide upon G based upon how you think you can best model and represent that data.
More questions? Yeah, Shihab. Can you throw the mic? Yeah. But people need to hear.
I can hear you, but I don't know if there's people online, Kat.
Because there are people on Zoom. Yeah.
Thanks for the nice talk. Just maybe I missed it. So your observable, I think it's fine, right? How smooth it is, because the Milstein has some issues with the kurtosis. I mean, if you don't have the required smoothness, and this makes the things non-robust, right?
Yeah, there are many assumptions I never showed you. Yeah, I mean, I'm assuming that the test function is bounded to Lipschitz. So you basically, essentially, it's like you think about the signal x itself, and then the associated drift and diffusion coefficients are very regular. So if you, for example, to follow up, if you just think about the signal x and you change some assumptions on the drift and the diffusion coefficients, the coupling collapses completely. This method is useless. I mean, I'm not trying to say, I'm trying to say under these assumptions, there is a class of models where you get improvements, and there's a class of models where this is not very useful. And that's fine. So I mean, I understand exactly what you're saying. So the function var phi for me is very, very well regular and very, very, very nice. Otherwise, I get nothing.
Thank you.
More questions, maybe from the audience on Zoom? Okay, yeah, you have another question? No? Okay. So let's thank our speaker again. Thanks, Ajay. Have a nice day.